Log on, tune in, find out. Another good idea from Cambridge.
Cas from ETH Zürich is going to talk about key exchange.
Thanks a lot. Can people hear me in the back? Okay, thanks a lot. So this talk will be about key exchange, both on security notions as well as automatic analysis. It might have been called also Cas's Magical Adventures in the Land of Key Exchange. We'll get to it soon. Okay, right, sorry, almost forgot. This is joint work with David Basin, Michelle Feltz, and Simon Meyer at ETH Zürich. So this is my roadmap for today. It's appropriate for just after lunch, I think. On top is, the top axis is towards modeling. Bottom here is towards practical threats. I'll first be talking here about key exchange models, what sort of security notions exist for that. Then I'll make a short excursion to practical threats that you may have on such a key exchange notion. I'll go back to formal analysis, and I'll end up with a short case study that I will try to relate the security notions that we have to a practical attack scenario. So first half is more my perspective on security here, and the second half is more on the work we've done during the last 3-4 years. Right, so what is key management here? So if you have long-term keys, this is convenient to distribute keys. It's convenient to have asymmetric cryptography for the fact that you need to distribute keys to parties. This makes management easier. This makes it easier to just make the initial setup phase much easier. What you actually want in practice when you want to communicate is you want to have symmetric encryption, so maybe short-term symmetric keys. And the connecting part between the two is the key exchange protocol. So no matter how secure your long-term keys are, no matter how good your symmetric encryption scheme here is, if the connecting block is not working, you have a problem. So classically, there are a number of protocols for this. Say there's Diffie-Hellman, but this is somehow, say, state-of-the-art still in key exchange. This is the MQV or HMQV protocol. I just want to give you a flavor of what sort of protocol I'm talking about. So it's very simple. A generates a random X, sends G to the X to the other party. B responds, sends G to the Y. That's it, right? The tricky part comes in the key computation. So what happens here is A has a long-term private key, small a, and B has a long-term private key, small b, and their corresponding public keys are G to the A and G to the B, and there is a complex key computation that combines the two. And the upshot of this should be that only the intended communication partner should be able to compute the key. Okay, there's two variants here at least, but in literature we'll find even more. So there's even these values D and E going on. These D and E are publicly computable values. Oh, right, get back to this. So D and E are publicly computable values, and they change over the protocol. They're meant to break the relation between the inputs and the outgoing key derivation function. What happens here is that Alice receives G to the Y. Sorry, yeah, right? Sorry. Right, okay, I'm back. So Alice receives G to the Y from Bob, right? That's the randomness, G to the power of the randomness generated by Bob. What he does is he multiplies this with the public key of Bob, raise it to the power of E here. The whole thing is then raised to the power of X plus dA, which are somehow the private components that Alice has access to. And by symmetry, B does a similar computation, and what he ultimately compute both here is G to the X plus dA, which is somehow Alice's private half for Alice's session, and Bob's half, Y plus EB. Right. So what is now the desired property here? Ultimately, what we want to show is that the key that Alice and Bob compute cannot be distinguished from a random key. Right? But something is going on here. Why is this such a complicated protocol? Maybe we could do something much simpler. What happens is that we're talking about a fairly complex system. So there's multiple network messages going on. There's stateful programs. If the initiator, Alice, sends a message, she stores their temporary state and waits until the response comes back. There's long-term keys, short-term keys going on, and they both compute intermediate computations. Now the trick is here, what exactly do we allow the adversary to do? So a security model in key exchange somehow describes how this adversary interacts with this complex system. The classical notion is from '93, which is by Ballara and Roggeway. So most of you might be familiar with this notion. The security notion models the interaction between the adversary and the agent in the system. And there's two ways that is done. These are queries or oracle queries as we know them. So what the adversary can do is he can do a send query, by which you can activate sessions at a certain agent, or you can get the response according to the protocol on a message that he sent. And there's something called a reveal query. So here the attacker is assumed to be able to compute certain session keys, or maybe because he learns them, or maybe by a brute force attack is able to compute session keys. And what we like to establish is that from one session key he cannot compute another. Yeah. So in order to model this in the security notion, there is this reveal query. Right, so what does it look like ultimately? There is a game defined for the security notion. The adversary may do these send and reveal queries, interacting with the protocol and getting certain session keys. At some point he chooses a particular thread to attack, or a particular local session to attack, which we typically call the test session. A bit is flipped here, or a coin is flipped, and then the adversary randomly gets this session key, or he gets a random string from the key space. What's disallowed, of course, here is that the adversary may not do a reveal of the session key of this test thread. Obviously, then he gets the exact key that he wanted, right? And ultimately, the adversary has to guess B. This is common setup. And if he can do better than guessing for this particular bit, then he wins the game. Okay. So this is the classical notion. And when I started in this field, I figured, well, I just read the literature, there should be solid notions, everything is fixed, and I can just encode this for my formal analysis tools, and I'm done. Right? It turned out to be not so stable. So there are many new notions. So one very famous security notion for key exchange is the CK2001 model. It adds queries for corrupt, for long-term key reveal, but a particular thing it adds is the session state reveal query. So what this does is the following. So Alice, when she's computing this, she's doing exponentiations and additions, so she's also computing intermediate products. And what can happen is that, let's assume that we have our long-term keys stored in a secure module. Right? But for efficiency reasons, these other computations are done outside of the secure module. It may be the case in this threat model to this saying that the adversary is not able to get into the secure module, but he is able to get this unprotected memory. So he might be able to get intermediate computations. So that's what this is trying to model. So, okay, now the question is, how close is this to reality? So this model has been used for quite a long time, but there are some obvious questions you can ask, right? So if this really is your threat model, and you think your keys, your long-term keys are safe in the secure module, right? Then why are you only modeling read access? So when I think that some adversary may be able to get into my machine, but not into my secure module, I would actually assume that he's also getting write access. So, and let's put it around. I don't know of a practical threat scenario, a realistic one, where actually the adversary is only capable of reading this local state. Or even worse, execution access. So once the adversary gets into my unprotected half of my machine, but not in a security module, why couldn't he simply interact with the API of the secure module, right? We would end up at API analysis. So somehow, this state reveal query would only make sense if you have a secure module. Because if you don't have a secure module that protects your long-term keys, then this is not an issue. The adversary would just take the long-term key and run off, and he can do everything. So given that the only context in which this model seems to make sense is when you have a secure module, it seems to be somehow a weak approximation of what the adversary would be able to do. Okay. Some years later, there's another famous model, the so-called extended CK security model in 2006, and it removes the session state reveal query and instead introduces the ephemeral key reveal query. So what is this supposed to do? Now the adversary gets access to essentially the randomness. It's called the ephemeral key because typically in a Diffie-Hellman protocol, this is the small x and small y that you saw, that the randomness that the agent generates. So what sort of threat model is this sort of modeling here, right? This is the question. So I tried to find examples of concrete systems where somehow this would reflect what is modeled in ECK, in the extended CK model. So for example, there are people who would sell you a quantum random number generator. So then the idea is that the randomness is very strong and it's not wrong or not broken. It's very well generated randomness and not predictable. Similarly, there's a product called something like an entropy key, which is a USB stick, which should effectively give you good randomness through your USB port into your Linux system. And this is actually what is modeled by this query, because the adversary, he is getting the right randomness, the randomness is generated in the correct way, and once it's generated, he gets it. But this is already not a good model of this system. Because in this case, the idea is that the randomness from the USB key goes into your randomness pool before it is ever used. So it sort of adds random values at startup to the randomness pool. So in the model, in the extended CK model, the adversary can only learn the random value once it's actually being used. So it's not a very accurate model. So this prediction that you might have when you're attacking here, this system, is not really modeled. Right. But still, you can wonder, can't the adversary influence the random number generator? Right? So there's the same with predicting values. But more cases actually occur that the randomness is just bad. So if you start looking what the threats are on randomness, the main randomness threat is simply that your random number generator is broken. It's just not giving you good randomness. That's the main threat. So let's make a little excursion to a concrete system. Right? This is the famous Debian fix of OpenSSL. Who is not familiar with this? I think most people have seen it. Let me go through it because it's somehow funny here. There is a bit of code in OpenSSL that is meant to retrieve, to give you random bytes. So you can ask it for a number of random bytes. And some buff variable goes in. So this particular buff thing is to add entropy to the randomness that you get. You may use it or you may not use it. The function works just fine if you don't use it. But what's the problem here? When it is updated, when buff is actually copied to M here, it can be the case that it's sometimes called with uninitialized memory. This is the way it's implemented. The implementers maybe thought that it might be good at some point to add some random entropy. It couldn't hurt. The function works fine if you take it away, but this is an option to add entropy like that. Just put in uninitialized memory. Notice that it's protected here by this if ndef purify. So if you use a debugger, say valgrind or purify is another tool, then what you will notice that it will tell you that sometimes this particular thing is called with uninitialized memory. So it would complain. So that's why this is there. So if you want to use the tool to analyze this program, you should sort of put this switch off so you don't get the error. But people complained since 2003 saying, I'm running valgrind on the code, there's something going wrong, right? Can you please look at it? Okay, so somebody set out to fix it. So here's the concrete patch. So here is this thing I was talking about. It says purify complaints, it's protected. The green stuff is added. Can people in the back read that? It's probably hard. Okay, so let me tell you what's in the green bit. So here we had this MD update that I had on the previous slide. So in some cases this can be called with an uninitialized memory. And so what the programmer added here is a commenting out this particular piece of code saying don't add uninitialized data. So far so good. Nothing goes wrong here. Oh look, there's another one. Let's get rid of it too. Right? So here problems start. Let me tell you what this first bit does. So this first bit is the exact same piece of code, but it is not protected by this purify comment, and it is actually in a different function which is called randadd. And the purpose of this function is to actually seed the randomness pool. And how it does that is to take the buff variable, copy it into M, and then you get essentially the system's entropy, say from the kernel or whatnot, is copied into the SSL system. So what's happened effectively is that all the entropy coming from the system is no longer copied into the seed of the randomness. It's completely gone. The only reason why this wasn't detected immediately is that the process ID is still going into this function. So if you look at the output, there's still seemingly random values coming out, and you know how people test randomness, right? So nothing done here. So the net effect of this is that this patch stayed in and nobody noticed. So between 2006 and 2008, Debian and all its direct derivatives that were up to date were having only seed for the randomness was the process ID, which is 15 bits on a normal Linux system. That's the only randomness going in. So what you can do is you can just pre-compute all long-term keys generated in that period, and that's what people did. Right? So after this, people had to update all their keys. But even if you had a key that was outside of this period, when you were actually using OpenSSL, the randomness, like the small x and y in a protocol, are still coming from these 15 bits of entropy only. So that's very small. So is this well modeled by ECK, right? I'll get back to it later. So, second part here. My background is in symbolic analysis of security protocols. And end of 2008, I figured I might as well take some notions from key exchange, put them in the tool that I developed, and write one paper and be done with it. So I ended up working until now on ongoing projects, working on this, and been doing a lot of stuff in key exchange as a result. So I want to give you in the next 3-4 slides a little flavor of what's going on in the background in this. So in symbolic analysis, we model cryptography in a black box way. We like to get rid of all the complicated stuff, so we'd only talk about black and white things. Either the adversary can learn something or he can't. And we assume that the cryptographers have done an awesome job and given us perfect components. So what we assume is that if you have an encrypted message, you don't learn anything from it unless you really have the key. So this is encoded here by this type of rules. So these are inference rules. So there's a horizontal line. On top of the line is the premise. So if the premise holds, I can conclude the thing at the bottom here. So this says, suppose I have a set of messages M, and there's some term T in it. Then I'm defining that the adversary can infer, that's what this symbol here means, the adversary can infer from M the term T. Right? Now, if an adversary can infer two terms, he can also pair them. Simple operations. Here it becomes more interesting. If he has a term T, he can hash it. If he has two terms, he can do, say, encryption with them. Encrypt term T1 with T2. And if he has a term T1 encrypted with T2, or he can infer this, then with the inverse, which is somehow, think of it as the decryption key, then he can actually infer the message T1. However, the other rules are missing. So critically, if he has hash of T, there is no rule that applies that would give him T. Similarly here, if he has this encryption, but he doesn't have this inverse key, there's nothing he can do with this. Now, there's a lot of research going on the exact relation on this, and it's not so clear even that well, it's actually not true that there is an exact mapping between this sort of symbolic model and real cryptographic components that have been proven secure. That's out of this scope of this talk. But in itself, it's a very interesting theory, and it's a very powerful tool. From your context, I would say it's a very good tool for attack finding. Right? Even if you don't know exactly what the guarantees are, if you would in such a system prove something, at least for attack finding, this is useful. So, yeah, sure.
How do you get the inverse key? Can you get that from the key itself?
No. Well, depends a bit on how you model symmetric crypto versus asymmetric crypto, but no, you can't get it. So if nobody sends out the decryption key, you would never get it.
But I mean, in your model, how do, like the model is supposed to capture, how do you get the key?
So initially the adversary knows certain messages, and as we'll see later, he will interact with the system and the agents will send messages, and from that he can see what he can derive. So typically in such a setup, he will have one private key of the corrupted agent or something, and from that he can start to try and build. Right. But I think you'll see it in the example. Right, so now let's see what these terms look like. So suppose we have a set of agents and a set of freshly generated, say, random constants, a set of variables, here a constructor for terms, pairing, and here a constructor for encryption. So maybe we can add other things like asymmetric encryption here or signatures. Then we specify the protocol in sets of roles. So there are various frameworks to do this. It's just a framework that's the back end of the tools I've worked on. So we have a set of agent events. So an agent can here start a particular session or a particular thread, and we have a notation for that saying that some agent started a particular role. Then he can send a term. So this is encoding for sending a term from one agent to another. This is receiving a message apparently from some agent. And additionally, we have commands to encode, say, annotations. So these red things here are just to annotate our protocol specifications. So one thing is here that we said we can annotate that we generated a certain set of fresh values. We can annotate that the protocol state is a certain set of messages, a certain state, which will relate to this session state review later. And finally, we can annotate that there are a certain set of session keys. Okay, very simple example here. Suppose I sends to R in a protocol specification his name, some fresh key encrypted under the long-term symmetric key shared by I and R, and the response is some fresh message M encrypted with this temporary key K. Right. So what would it look like? Saying that here, for the protocol, the role I is defined as we generate K, we send this message, and we receive R, Y here. And if you look there we said that R sends to I a message M, right? That's what we see in the specification for the second role. But when the initiator role receives this, he receives this into a variable. So that's what Y is encoding here. So Y is here a variable, and of course in our ideal world, I will be instantiated by M. Right? But this might not be the case once the intruder starts to interact with the system. Okay, so once we have our protocol specification up and running, we need to define how this is somehow into a concurrent system interacting with the adversary. Right? So we assume that a protocol can be executed an arbitrary number of times. So this is done in so-called threads. So think of it in terms of key exchange models as a local session. So a thread is sometimes called here a role instance or a local session. So any agent may start any number of threads of any role of the protocol. We don't assume any bounds on that. And we assume each of these threads a unique identifier from a set. And what we do is then we bind these locally freshly generated names and variables to this particular session, right? So this somehow encodes the local memory of each of these sessions. So if you have here the initiator role of this protocol P, then when we instantiate it in a particular thread, we syntactically extend these names with their with basically their scope or their particular thread ID, differentiating between the different variables and constants. Okay. Now we have a mechanism on the next slide. This is the last technical slide on this. In order to measure progress now in our system that we're going to define, we have a sort of a program counter. And the program counter here is a mapping saying that each thread still has to execute the following events. So initially, of course, a thread has to still execute all the steps of this protocol role. And as we progress through this, we eat up the events that we have already done. Okay, so then the simplified model here, we set up a transition system that will generate all possible behaviors here of the interaction between the intruder and the protocol. So this transition system has a state, which is a trace of events that has already occurred. The initial knowledge of the adversary, or the intruder knowledge here, and this program counter set. And then this is the basic system. So what happens is the following. If you have a state in the transition system modeling this whole interaction, then you can do the following transition if some agent is about to do a send of a message. So what we have is that if a particular thread TID is about to send a message M, he can do so, this action is enabled, and what happens is that we store the fact that he sent the message in the trace, so in this sequence of events, and the intruder learns directly this message in this set, and we update the program counter. This is the core of it. There's only one additional step, that is if you receive a message, you do pattern matching. So what happens here is that if an agent is about to receive a message and he doesn't know what it is, he's about to receive something into a variable y, so maybe he's receiving a certain encryption, then he will here write, okay, I'm now receiving a particular message in a variable y, so the PT would be y. If the adversary is able to generate a message that fits this pattern under some substitution, and the substitution here is sigma, then actually the transition can fire. So the transition is then the following, the same as above. We just add the fact that it happened to the trace. The intruder knowledge is not updated here, and the program counter is updated, and the variable as we received it is now stored in the state of the subsequent steps. Okay, that's really it. So now you've seen the core of the model. Right, now suppose you have a simple protocol here, A sends to B n, right? Then this is a possibility of a reachable state. So it can be the case that A sent to B a particular n from this thread 1. Now, of course, after that has happened, the intruder knowledge has been extended with this particular n1. The intruder immediately learns it, and the state is updated such that thread 1 now no longer has any remaining steps, but it may still be that thread number 2 can receive in the next step in some variable this particular message. Okay, that's it. If you have such a system, you can now try to see what sort of behaviors are possible and what sort of judgments can hold in this. It looks fairly simple, but already in this case, the general reachability properties such as secrecy are undecidable. And even if you bound the number of sessions or threads, even then the problem is NP hard. But we have pretty good tools to work in this setting. Okay, now getting back to key exchange, right? So in key exchange we had these queries, and now we're going to actually model these queries in our system. So for example, if we want to model the fact that the adversary is able to learn long-term keys after the test session is ended, which is what you typically model for a perfect forward secrecy property, then we add a rule. And the transition here is the following. We can do the following transition. The adversary can learn the long-term key of Alice, right? And it just added to the knowledge. So we added to the trace that this was revealed. So you can see this as this query. The adversary gets the long-term keys. But additionally, if you look into key exchange notions, there is something called freshness. So this cannot always happen. There is a side condition to it. For example, you can only learn it after the test session has ended. So we encode that as a premise. Right. So this encodes that the test thread has ended because the sequence of steps that it still has to execute is empty. Okay, similarly for a state reveal, there is a more complicated rule. So the bottom here is essentially the state reveal query as you would have it in the model, where the top half of the rule encodes the conditions under which this is allowed. So that is saying you cannot do a state reveal on the test session or its partner. So what we did is we took the queries that you have in key exchange models and we basically decomposed them into 7 rules. And now the idea is that you can recompose these 7 rules into sets of adversary capabilities, and you get a set of 96 models out. So now the question is, does this work? So far I've been working in a symbolic model, and you might think, okay, nice for you, good, right? You just modeled some stuff, does it work? Right? So we have extended our tool support with these rules, and there are some surprising results coming out. So if we now go back to the key exchange domain and we start modeling these small protocols with respect to these things, we actually find nearly all attacks. And let me tell you what we're not finding. We are not finding things like small subgroup attacks. That's to be expected because it's outside of the abstraction layer that we're modeling. But very surprisingly, we find all the other attacks that are around in literature just at this purely symbolic level. Maybe rephrased, maybe it is the case that most of these flaws are really logical flaws, and it's pretty rare that these depend on probabilities. So the design decisions that are being made, or the flaws that are still in key exchange protocols, are really logical flaws, and that was surprising to us. We didn't expect this. Additionally, we find quite a number of additional attacks that were not reported before. Now, to generate such a table, what you actually do is you model the protocols. If you're familiar with modeling it, it takes you, say, an afternoon per protocol if I'm on the roomy side. running the tools for each protocol model in each adversary model, we're talking here about maybe 10 minutes at max. So this is just feasible to have a machine run all these protocol models through all these particular adversary models, looking at what the literature says and finding quite a number of new attacks. And traditionally, if people find an attack, you write a single publication on this in this field, right? So this is pretty effective. Okay, what is also interesting is now that it gives you a means to take a given protocol and just have the tools analyze this protocol with respect to all your models and just see what comes out. So let's do an example. This is a protocol that was proposed last year, and it seems like everybody who works in key exchange wants to make a better HMQV. This particular proposal is by Cao and Yao in end of last year, and it's called the OAKE protocol, where O has one explanation is optimal. So this is optimal authenticated key exchange. What is happening? It's a similar protocol structure. They write that they exchange the public keys, but essentially the structure here is the same. You generate a small x and you send G to the x, and the responder sends G to the y back. Now the session key computation is quite different. There's again some constants, C, D, and E involved, but they can be publicly computed. So the adversary doesn't have to worry about C, D, and E in order to compute the session key so much. So what does the initiator here do? What does A do? He takes the public key of B, raises it to XD, where X is the value he generated himself. Here is the ephemeral public key of the responder, and this is multiplied similar to HMQV. So even if you're an expert, it can take you quite a while to stare at this protocol and find out what's going on or why this may be better or not. So the claim of this protocol is that it satisfies at least the same security as HMQV, but maybe there are some technical differences about whether it's gap Diffie-Hellman or what you need as an assumption. So that's the claim. So does anybody see a problem? There are some experts in the room, right? Might be able to see the problem. Okay, so we run it through the tool. It takes about an afternoon to run through all the models, and this comes out. For people who are in key exchange, this is a very ironic table. What is so ironic? The tool says HMQV is strictly speaking not correct in CK 2001, which might be ironic if you're not intimately familiar. And it says that there are no attacks found in this extended CK model for HMQV. So it's resilient against an ECK type adversary, but there is an attack on this OAKE protocol in ECK, right? So this directly seems to violate, at least at a theoretical level, that this OAKE gives you the same guarantees as HMQV. So what's going on? So this is what you could have done in retrospect if you know what you're looking for. And in fact, this is what I did after I read the paper. I did a little computation on the back of an envelope, literally, because I'm now trained to do this sort of stuff. But the point, of course, will be that if you don't know what you're doing, you can still run the tools and find out such attacks. So what's going on? Let's look at the key computation. So there's these D and E D and E and C things. So let's get rid of them, because the adversary can compute them from the messages he observes. Right? So if we get rid of them, this is what it reduces to. So just throw away D and E here and D here. Right. So if you write it out, you get the following. Now you see there's something that's not here that is here. So let me go through this, right? So this is what's called the static Diffie-Hellman key, this G to AB. This thing is the classical Diffie-Hellman key as it would compute it. And these are somehow these intermediate products that you have in HMQV, that you don't have in something like the unified model. Now if you look here, the static Diffie-Hellman key is gone. And the benefit of using this OAKE protocol was that it was more computationally efficient. You do some pre-computation offline, and that's why this is the selling point of the OAKE protocol. It's more efficient. Well, why is it more efficient? It's simply not computing everything that you would have in HMQV. And the practical upshot now is that suppose you learn X and Y. Well, here you have X and Y. You compute this. You have the public key of B. Everybody has it, right? You have X. So here you have the public key of Alice. You have Y. You have it. Now, on the other hand, if you'd have HMQV, you'd still have to have the static Diffie-Hellman key. So just X and Y would not give you the key. Okay. Now let's go back to practice here. So the upshot of just running this analysis, right, is that there is a big difference between these protocols at a theoretical level, and that is that if the adversary somehow learns the randomness, but he doesn't learn the long-term keys, then in HMQV you're still fine. You cannot compute any session key, but in OAKE you're in trouble. So can this happen, right? Well, let's go back to the Debian case. So suppose you had your key generated, your long-term key generated before 2006. Right? So you're fine. You're not updating your keys. And suppose in that period you were using either HMQV or OAKE. Right? So the fact that the randomness is badly seeded means that there's only 15 bits to guess. In this particular case, you'd need to guess both. You'd need to guess 30 bits, essentially. But given that an eavesdropper, basically who had monitored the logs, can now compute the session key, an OAKE. But he cannot get these session keys if you were running HMQV. Right? So I think this is, having said this, in reality, we're not using either of those in that period, so I probably guess that you could, with some hardware, and if you have the logs of somebody, you can produce just these session keys between 2006 and 2008 anyway. Right? Right. Another discrepancy here between the models. So what's interesting here? So we found an attack in ECK model that can be mapped back against such a random number generator. So although I was observing that maybe the extended CK model doesn't really capture exactly what's going on with leaky randomness or bad randomness, it's still the case that we can find such an attack. So that's surprising. This is a good thing. What is a bad thing is that here you see also some other discrepancies. This guessing of the bits, it doesn't really matter, right? If you would have to guess 8 values, right, this becomes a problem. So if you have to guess 8 random values to get the session key, you're in trouble. Whereas in the extended CK model, this is all equal, right? You either get all the randomness or nothing. So although there are discrepancies, it's still pretty effective in finding this type of flaw. Okay, conclusions. So the relation between key exchange models and practice is really not obvious. So to go back to the metaphor we saw in the first talk, I think this cat hasn't landed yet. Right. So there's still a lot to be done. I think there's a big gap between the input of the models here, the security models as they've been used, and what you would actually like to prove. So if you really want to prove something about a secure module, or you really want to prove something about bad randomness, I think these models are not really capturing what you want to say. Having said that, part of it is already pretty well captured. So we had this discussion before with several people. I would actually like to, personally I would prefer not to talk about provable security in the CK model. I would rephrase it as proving absence of attacks from the CK class. In that sense, it becomes much clearer what you're really guaranteeing. This is open for debate, maybe later for the panel. Right. The symbolic models that we have bridge quite a gap between the key exchange models and the formal models that we were using before, and they're surprisingly effective. It's really surprised us that we could find so many of the attacks, and we were expecting maybe to find a few, or maybe hopefully a few new ones, but that we're really finding everything at this high abstraction level except for small subgroup attacks is surprising to me. So once you have the tool support, it's not meant to replace in any way your security proof. It's a supportive technology. But given the speed at which you can evaluate your own protocol proposal or somebody else's, it seems good to use it. It seems effective to use it. It's a good tool for cryptographers too. And additionally, if you're designing a protocol, running it might actually reveal that you could prove more of your protocol than you were actually setting out to. Right? Because the tool might tell you, there's actually this other model where I think it's correct, you might be able to try that proof. Okay, then I want to end on a positive note. I didn't talk about standards yet. In some related work recently with similar technology, we looked at the ISO IEC 9798 standard for authentication protocol. It's a very different standard. And we did this work, I think a year ago, January last year. And we generated correctness proofs of our fixes, and actually to our surprise, I think these changes are now already coming up in the new version of the standard a year later. So I think that's a very fast process, and I think the meditating ladies from Tom's talk would have been appropriate here. So I think in some cases the standardization bodies can do a good job in quickly updating these type of things. So I think that was it. Thanks a lot.
Nicholas. So given that you have a way to specify like the security model, let's say the security model, is it possible to use a tool like that and do exactly the opposite procedure? So I'll give you a model and I'm searching now for a protocol that is going to be efficient in some way to satisfy exactly that security model.
It's an interesting idea. Oh. And we looked at it before. Somebody tried before to do protocol generation, but it turns out it's very hard to sort of sanitize the space you're searching. So what happens is you start generating arbitrary things. So for example, here in this setting you think, well, what's going on? Right, it's very simple protocols. You have some exponentiation, some additions, a hash. So you permute all the options, you have randomness, you may be able to generate this. So you could. So the short answer is you could do it. We haven't done it. We're afraid that the search space will explode and it will not really be sensible. And yet you could come up with a metric saying that having less exponentiations is more efficient, or trying to split up offline, online computations. To be honest, I'm now more interested at the moment in maybe changing the models first and then coming up with different protocols. So at the moment I'm a bit, I wouldn't do it anymore, except for this one paper we're still finishing. I would move away from this type of model. But then the same procedure might apply.
I have one question on the results from your model. If you show the previous slide. No, the one after.
This one?
No. It's about the corruption of the random number generator.
Yes.
As you compare the two protocols.
Right.
So the second last page.
Here. Yeah.
So what you are implying here is that if the random number generator is totally corrupted, and it's an MQV, HMQV is still secure.
Yes.
No, I don't think so.
Well, okay. Please explain, and then we can discuss.
I think there are many kinds of attacks on a protocol, and easy to come up with an attack and claim it breaks protocol. But there is a certain boundary, and within the boundary is what protocol can do, and beyond boundary is what the protocol cannot do. And I always thought the random number generator is outside the boundary. If you don't have a good random number generator, and then no protocol can be secure from the key exchange.
Well, what I'm saying here is that, and this is an interesting thing, if your random number generator is broken, let me simplify it. If suppose it only always returns 1, you're still computing using the static Diffie-Hellman key, or a variant of it, which is still fine. So if you don't assume any other threat, I think you're just fine. You're just having a static Diffie-Hellman key.
Yeah, I suppose the key observation is that the G to the A and the B have been generated with proper randomness.
Sure.
So, of course, if we hadn't had the proper randomness before, then
Sure. That's split in this particular model. That's split. So the randomness means the randomness of the local sessions. Yeah.
Any other questions or comments? Oh, yeah.
So these kind of tools really are geared towards finding logical issues.
Sure.
But things like using gap Diffie-Hellman or not using gap Diffie-Hellman. Using gap Diffie-Hellman is something that you can see if you need it or not from the protocol. Basically, the question is whether the protocol is giving you a Diffie-Hellman oracle, one of the keys. If the protocol is giving that to the attacker for free, then you must use gap Diffie-Hellman.
Right.
And that's something that probably you can find with your tools, whether the protocol.
It's a good point. I haven't looked at that.
I think that would be interesting because using gap Diffie-Hellman or not sounds like an algebraic issue, but actually it's a logical issue.
You didn't look at that at all. That's an interesting thought. Okay, thank you. No.
Any other questions or comments? Okay, let's thank the speaker again.